So today is the last lecture we're going to have on scattering theory, and we're going to take everything we've learned in Fourier space and then transform it to real space. That's the objective for today, is to essentially do a Fourier transform and convert all this momentum data into something a little bit easier to imagine. So as time goes on in your career, you'll start finding it easier and easier to think in momentum space. There is a certain amount of intuition you can build about functions that are described in momentum or Fourier space. So you should sort of have a feeling for what the Fourier transforms of smooth functions look like. And you should also sort of be aware that Fourier waves, the periodic waves turn to delta functions in real space and so on. So you should have this intuition, you should be building this intuition as you're going through your career, and at some point you would find it, I think every one of you will find it easier to sometimes think just in momentum space. But, you know, it's still pretty difficult to visualize things in momentum space, even when you've had a lot of practice at it. And scattering, I think, is a good example of this. It's all very well to know that the outgoing particles will have certain momentum pointing in certain directions. But this isn't quite the same as actually seeing the wave packet spread out from a scattering source. So if we have a scattering target here, there's some wave that comes in space now, not momentum space, but in real space. Then as time passes, the wave experiences this potential, the central potential, and then sometime later it gets scattered away from the target. And then there's some sort of residual particle amplitude that flies off. So it's this spatial picture. I hope you have this intuition already. I mean, if you've ever stared at a pond and you've looked at waves rippling across a pond and there was a leaf floating in the pond, then you will have already seen such a scattering process take place. Just go to simulate a pond in your sink and then generate some waves, and then you will see a scattering process taking place. We also experience scattering with light all the time. We have particles suspended in liquid, we shine lights at it, and what comes out, right, this sort of ripply interference pattern. This is another wave scattering process. And the spatial distribution of the outgoing wave here, this, call it psi scattered, and this is sort of psi I, whatever, the plane, let's call it P to be consistent with what comes later. This is obviously extremely useful if you want to compare to an experiment, because in an experiment you really have access to mostly spatial data. It's not quite true. I mean, if you build a detector here, then the detector can be sensitive to the momenta, but what momenta comes in here is more determined by the spatial wave function rather than the momentum space wave function. So that's the objective today, to just, in quote marks, to just do a Fourier transform of what we've learned so far. But it's a Fourier transform worth doing because it allows us to connect these wave functions with things that we could build in an experiment, just a touch easier. And these Fourier transforms are a little bit tricky to do because we're going to use spherical polar coordinates. Makes life slightly difficult. But in principle, we're doing nothing other than an inverse Fourier transform. So let's look at the stationary scattering states as a kind of warm-up to understanding the full scattering process in real space. Let's just look at what the stationary scattering states look like in real space. So we're going to look at this position wave function for the stationary scattering state. This wave function. We already know the equation that these stationary scattering states obey, so this shouldn't be too difficult. So we know the stationary scattering state, or improper state, obeys this equation here. All right, we've already proved this in a previous lecture. And to get the wave function, well, I've left the appropriate gaps here so that we can get the wave function out by taking the inner product with x. So let's do that, right? This is the thing we want on the left-hand side. Well, we did that here, so we better do that there. And then we're going to put an x in here. Okay, that's not quite what we want yet. But we can get this fully described by inserting a completeness relation in there. So now we've got the object that we want. We've got an integral equation for the object that we want. This is this thing here. We know this. That's easy. And in fact, we know a bit more, right? Because the potential applied to a position eigenstate, well, the potential is diagonal on the position basis. So that's actually easy, right? We can just walk this ket through and then evaluate the potential on that position there. So there we go. That was pretty easy, actually. We have an integral equation for the wave function of a stationary scattering state. I think I'm missing a naught somewhere here. Yes. It's G naught. In fact, we can do even better. We know this as well. Although, yeah, that's where we're going to have to work a little bit hard today. It's not trivial to work out this thing, but it's not ridiculously hard. So we know this, we know this. So the plan of attack for today is to first understand what a single stationary scattering state looks like in position, and then to describe scattering processes. They're really a superposition of a bunch of these stationary scattering states, and then we just look at how these things evolve in time. The superpositions of these evolve in time. That's the strategy for understanding how it's all going to look. Right. Well, let's start with the hard. I mean, whenever you see something like this, I guess there's two schools of thought on how to solve a problem. One is you do all the easy stuff first, and then you leave the hard stuff to the end. That's, I suppose, the optimist's version of solving a problem. I'm sure it'll be fine, so I'll just do the easy stuff first. And then there's the pessimist's way of doing the problem, which is like, oh, it's so hard. Let's just tackle the hardest bit first, and then if I fail there, then there's just no point. There's no point in going on. So this is, we'll do it the pessimist way. So the hardest thing in this whole equation is this G naught, right? So let's look at that. And the thing is, we know how to diagonalize G naught. G naught has a, what is G naught? Well, it's, just to remind you, it's the inverse of the free particle Hamiltonian. It's just that, right? And the way we're going to evaluate this is we're going to first go to Fourier space. G naught's then diagonal in Fourier space, and then it should be all easy. So let's just stick in a completeness relation in here. So far, so nothing. All right, we know that H naught is diagonal with respect to the improper P basis. So that the inverse, this is an identity operator here, so that the inverse of this operator is also diagonal in the P basis, so we can just substitute in its evaluation at P. And then we are more or less done. X, P, P, X prime. So I'm passing this P all the way through here. And that's the expression we have to cope with. And this we already know, right? We know what momentum, improper momentum states, what their wave functions look like. It's e to the minus or plus. Let's see what I decided on. I liked e to the I p x minus x prime. That's what I liked. Minus ipx. Okay. So apparently we're sticking with this convention for the momentum space wave function. And there's some 2 pi's, right? Because there's a 2 pi in this amplitude there. Okay, so that's just a triple integral. This thing here is just p squared, right? This is p, it's a triple integral with an exponential and something on the bottom. It's not trivial to do this integral, but it's doable. It's doable. There's a variety of ways to attack an integral like this. We're going to use contour integration today, but you could even just discretize it and put it into a numerical integration package. I've done that. It's works surprisingly well. But what we want to understand about this integral is not what its exact value is, although we can actually integrate it exactly. We want to understand what does this integral look like when x is very large. So the limit we care about in scattering theory you remember, is the t is very, very, very large limit in scattering theory. And in space terms, I mean, if a particle is traveling velocity v, so if the group velocity of a wave function is v, then what does this limit imply in terms of space? So, v is meters per second, right? So we multiply by time. So displacements, the limit of displacements that we're interested in is really vt is very large, or simply x is very large, where x is measured relative to the scattering target. So we don't care what's happening in the intermediate times where the particle is near the scattering target. We only care about what happens when x is very far away, when the initial particle wave function is far displaced from the target, and when the final wave function is far away from the target. So we're really going to be focusing on that limit here, where x relative to the target is very, very large. And that allows us to do a bunch of approximations that will justify this picture I drew right at the beginning. Let's get started on this nasty integral, nasty-ish. Now we're going to anticipate that things are going to be somehow radially symmetric. We have this scattering target, right, whatever it is, right, some particle, and the scattering particle comes to the target and then flies away. And this scattering target, we've assumed from the outset that it's spherically symmetric. So we're going to imagine that the really important coordinate system is the spherical polar coordinate system based at the scattering target. So we're going to let this be the polar axis of a spherical coordinate system. So I'm now going to reintroduce these lines underneath, because to remind you that these are vector quantities. I mean, they've been vector quantities throughout, but I just haven't put the underlines under them, so you always know x is an element of R3, x prime is an element of R3, p is an element of R3. Right? These have always been vector quantities. So we're going to let this be the polar axis. I think this is a trick that you must have seen dozens of times by now. You build a coordinate system around this vector here, and then you look at the exponent here, right? You've got a dot product of two vectors now. So we know that the dot product of two vectors is the length of the first vector times by the length of the second vector times by cosine of the angle. Guess I'll do it this way. There. Just evaluating the dot product of two vectors. So the integral then in spherical polars gets a bit simpler. This is a sort of manipulation that you would have done several times in several different courses. This kind of integral turns up quite a lot. It appears fairly often when you do these, when you're looking at two particles, when you look at bound states, helium, two helium atoms, then you also encounter something like this. And so I assume you've done this integral once or twice in your life. It doesn't hurt to do it again. So if you carry out two of these integrals here in the spherical polar coordinate system, then you're left with one final one here. And it's this one that we need to do some contour integration on. So already, by looking at it, you know the poles are at plus minus I to mz. And so we know how to integrate this by the Cauchy integral formula. It's already just substitute in q as root 2mz into here. And there's two residues you have to worry about. And so the answer is just going to be characteristically simple. Now you could do contour integral. I mean, there's other ways to do these things. It might be a clever substitution, but I don't see it at the moment. There it is. Really wasn't so bad. Yeah, good. Now recall, what is star? Star, star. Let's have a look. So star is the Green's operator evaluated between x and x prime. But that's not actually what we want in the equation for the stationary scattering state. Let's call this equation I. So in equation I, we don't care about a general z. We just care about z that's equal to EP plus I epsilon or minus I epsilon. So this guy is the guy we actually care about. We just substitute in EP is plus minus I0 into here. And we have a square root here, so we're going to get different values according to whether we approach the branch cut from below or above. P, it's really P. So that's what that equals when you substitute in the limit that you need in equation I. So that looks remarkably simple. And when we substitute this into equation I, which is our next step, we're going to derive a constraint on the structure of the stationary scattering wave function. All right, so this is it. This is the equation that determines the wave function for the stationary scattering state. It's still an integral equation. We haven't solved it. So life hasn't gotten that much easier. But we also haven't used some crucial information that we have. So we know this, we know this, we know this, we don't know that. But we know something. We know something very important about V. V is meant to be short-ranged. It's meant to decay to zero rapidly. So let's actually exploit that information. So we're going to make a approximation, a statement that's only approximately true, but sort of good enough to get the result we're interested in. Let's assume that this potential is really just exactly zero for some radii that are bigger than some number. Some number A, some sort of like Bohr radius or something. In that case, this gets a lot simpler, right? Let's just imagine what's going to happen if we implement this approximation. So this is the spatial scattering wave function, the thing we want. This is the unperturbed in-state wave function. Then we've got to sum over all of space this funny phase factor, which is suppressed a little bit by distance, but not very much, times by this function here, times by this object here. Now, the fantastic thing about this approximation here, it says you don't have to integrate over all of space anymore, because the potential is just zero almost everywhere. So all you're left with is an integral over a little patch of some function which is more or less bounded, times by another function that's definitely bounded above by 1. So whatever comes out is going to look like a plane wave plus some integral which is really only focused around x prime equals 0. And the first bit is easy to understand. We know how to draw pictures of these things. We just have to understand what does this guy look like when x is near 0, when x is very close to the origin. And to do that, well, we'll just expand. We're going to expand this separation between x and x prime in terms of r so you know that if you take the dot product of x and x prime, then you can always do this. And we can put that expansion into this integral up there. So let's see how I did it. Yep. Just pop that expansion into the exponent. Just this function goes up there. And this thing here is the unit vector direction of x. So actually, you can more or less read off the answer now. The limit we care about is r is very, very big. And the integrand there has got some strongly oscillating term times by something more or less bounded times by something more or less bounded. So it's like some number. Some number is the integrand times by e to the IPR. And e to the IPR is a spherical wave. And let's just implement this limit r goes to infinity just to see what comes out at the end. Well, we get our plane wave contribution. That was guaranteed from the outset. And I've just rewritten this integral here in a quantum notation there. It's the same thing. But now we're going to exploit something that we know about matrix elements of the potential. So they're equal to this f transition function. So this is essentially the differential cross-section here. And here's another contribution. So the first part's the plane wave contribution. That's where nothing's happened. And the other part of the stationary scattered wave is a spherical wave. So now we have ourselves a limiting picture of what this stationary scattering state looks like. It looks like a normal momentum state with a spherical wave superimposed over the top. So this, I hope, gives some justification for the cartoon I drew in the previous lecture. So I'll just draw a cartoon of this wave function. So here's the scattering target here. Somewhere near here, then in this region here, we have no idea what's going on because these approximations don't allow us to conclude anything about the stationary scattering wave function here. But far away, we know that it's It looks like a plane wave. And also far away, where r is large, it looks like a spherical wave superimposed on it. But this is modulated around these peaks and troughs by this f here. So it's not exactly perfectly spherically symmetric. So asymptotically, every stationary scattering state, you can think of it simply as a contribution of a plane wave and a spherically spreading scattered wave on top. So this is all so far, this is not a dynamical statement, this is just the wave function of this stationary scattering state. Time is playing no role here. We're just looking at what this wave function looks like. In order to understand how a scattering experiment proceeds when you introduce time, it's the particle wave packet comes in, it hits the target, and it diffracts around it and spreads out over time. We're going to have to do a couple more calculations to understand a scattering process in space and time. Let's focus now on the process itself, on the dynamics of the system as time passes. Let's go right back to an in state in the scattering experiment. So we can express an in state as a linear combination of momentum, improper momentum eigenstates. And suppose what we're going to try and do is imagine a semi-realistic scenario where this in state is sort of strongly peaked around a given momenta. So we've given the particle a kick with as good a focus momenta as we can. And this peaked momenta is parallel to the scattering axis. So I better draw the scattering axis right now. So draw the experiment. Here's the target. So the target has some characteristic width A. This hasn't changed, same number as before. And here's the scattering axis. Let's call the scattering axis K. We have the scattering wave function, which is some blob that flies in at some velocity. And it has a width B. the width can't be zero. You can't have a fully localized particle in momentum and position, so it has to have some delocalization. And then we're going to imagine that we have a detector up here, and that's a distance d away from the scattering target and angle theta. So I think I've defined everything that's on the board now. P naught, B naught are just related by mass. So that's the initial state, right? Far away from the scattering target at time t is minus infinity. The particle is in this wave function here. Let's just see what happens as time passes. We know that the wave function, the free wave function, as time passes, well, it's easy, right? You just integrate Schrödinger's equation for the free particle. It's this part here. So time passes. And we know that the Hamiltonian is diagonal in the p basis, so we just pick up a phase on top of this wave function here. Okay, the wave travels. It's a traveling wave solution. And what's its group velocity? Well, we need to differentiate the dispersion relation to find out. So how fast does it go? Right. As written here, EP is p squared, so it's sort of not 100% clear how fast that wave packet is going to travel. To make this rigorous, we need to do a stationary phase argument, but this is not so challenging in the present. So what's the group velocity? You differentiate the dispersion relation and you end up with that velocity v. So we're going to expand the dispersion relation around this point, namely the point, this is the stationary phase part of the argument now, we're expanding this exponent around p naught, which is where the wave function is focused. Oh yeah, I haven't defined some notation. Better do that. Okay. E naught is E, the dispersion relation evaluated at our in momenta. Good. That's where we are right now. Now we do the stationary phase argument. Actually, I don't think we need a stationary phase. Since phi is so sharply peaked in momentum space, we actually don't need a stationary phase argument. Yeah. Yeah, we're not even going to use a stationary phase argument. We're just going to use the fact that phi is localized in a very tiny region around P, and that this function here is dominated by the Taylor series around P naught. Substituting in the Taylor series in the exponent. And then, well, this thing here is only non-zero near P naught. It's just a little exercise to check that in this limit, the input wave function propagates like a wave. So far I've just been telling you basic wave mechanics. Right? If I have a solution to the wave equation and it's peaked around certain momenta, then it's just going to translate in time according to its group velocity. So that's more or less first year physics. And now we want to, I mean, I'm not going to get a fully general answer to what the scattering process looks like for all time. We know, of course, we can't say anything when time is some constant. So what we want to do is just get a coarse approximation to what the dynamics of the scattering process look like as time passes, and we're going to do that by making a bunch of assumptions. So firstly, assuming for when time is very, very, very negative, infinity, that these constants obey these three relations here. So the width of the scattering target is much smaller. This is crucial. The width of the scattering target is like a grain of sand. The impingent wave function is fatter than that, right? This is what that is. And that the detector is very far away from both of these two things, these two scales. That's the most important assumptions to derive what we want. I mean, because if we had that the scattering target was much bigger than the width of the wave that came in, or the wave packet that came in, then the wave packet would have some pretty horrible, complicated interactions with that scattering target. In this limit, the scattering wave packet just sees the scattering target literally as a teeny spherical grain. And this limit here allows us to wait a very long time before we observe the particle, the outgoing particle. A second assumption just sets the zero of time. The wave function, wave packet's going to hit the target at time is 0. Not at time is 50 or time is minus 1,000, but time is 0. We're not going to get away with just looking at the free particles. We're going to have to deal with interactions somewhere. So the full interacting Schrödinger equation solution we need that. Here it is. If you remember, the Miller operator applied to the in state gives us the full interacting trajectory, and through intertwining we know that it's going to pick up this phase. Now let's find out what this looks like very far away. So for time is bigger than 0 and radii much bigger than the size of the scattering target, and radii much bigger than p times a squared, a limit that will become clear in a second. Okay, we've done this one already, right? So this object here we understood from this is just the wave function, and we've already understood the structure of this stationary scattering state. And we know that it's a plane wave plus a spherical wave modulated by something that's essentially the differential cross-section. So we're going to exploit that to just write this as a sum of two contributions, right? So we have psi in x and t. I mean, you just look at this thing here, phi p e to the minus I e bt e to the ipx. That's just the in state. It's going along unperturbed. But we pick up a contribution from what we'll call the scattering state. That's the second contribution in this integral. And now we'll make a couple of assumptions that are maybe more questionable. So this amplitude f, it might not be differentiable, right? It might, as you change x and p. There's no particular... We haven't derived any guarantees on the smoothness of this f. Might not be differentiable, but we're going to assume that f is differentiable. Now we know what this thing is. Psi in is just a plane wave. We've already seen that it's a plane wave that's moving at its group velocity. Easy. What we care about is what happens to this scattering wave. What does that look like as time passes? Well, if phi p is extremely localized around p naught, remember we assumed that the initial wave function peaked at p equals p naught. Okay, that's what phi looks like. In Fourier space, in position space, it'll be heavily delocalized. It has a width b. B is roughly the inverse of its width in momentum space. Then if it's extremely peaked and f is really smooth, then f doesn't change very much over this interval here. So we can just do the classic trick of just substituting in p naught into here. Of course, you make some error. I leave it up to you to check that the error that you make is about that. So then if you look at that thing there, I mean, this is a huge simplification, what we just derived here. This is just the original plane wave, but evaluated at rk. K is the vector along the scattering axis. R is current displacement. T is time. So another way of understanding the scattered wave is as some radially decaying function times by the in wave function evaluated on the axis. So after the scattering event, here's the target. There's a thin shell, thin-ish shell, a distance v0 times t away from the scattering target. That's just momentum conservation. And here's the detector over here, a distance d away. Now, will the counter click? Will the particle detector click? When does it click? It better not click when t is too small, because then this scattering wave hasn't had time to reach the detector. So let's just confirm this. So if the detector is far, so that relative to the width of the incoming packet, its distance is much bigger than b, then the probability of a count event or a detection event well, that's given by this function that we introduced long ago. So this function here is measuring the probability that the detector clicks when the initial wave function is phi in a solid angle d omega. And we derived an expression for this, but we don't even need to refer to that. It's just obviously this. This is just the scattering amplitude in that. Oh, that's a row. That's the impact parameter here. And what we're going to do now is randomize over this impact parameter, rho naught. So remember, impact parameter measures the distance from the axis k. Yep.
B was more or less the variance of the peak, right?
B is the variance. The question is, was B the variance of the initial peak? Yes.
So why does it have to be so much smaller than the distance from the detector to the...
So D is, so one of our initial assumptions is that A is less than B is less than D.
Right.
And so when theta is, we're going to focus on a regime where theta is a constant. And so we don't want the regime where theta is so small that this is then comparable to that. So that regime, because the detector is super far away, that would mean the detector is basically on the axis here. But that's the one event that we want to exclude, because we know that we're going to get a non-scattering event, right? There's, in fact, a majority of the amplitude is going to ride along this k-axis unscattered. But that's kind of a null event, so we want to exclude that. So yeah, I guess I didn't write that. We're going to exclude the k-axis by this assumption. So we randomize over impact parameter. We imagine that we're shooting particles at the target with a kind of Gaussian random distribution over impact parameter. And then we'll finally be able to connect this all now to the scattering cross-section. So this and this is an exercise. Good. So the summary the scattering cross-section is proportional to the in-state evaluated at time t, and the space-time structure of the scattering process is comprised of two terms, right? There's this plane wave contribution and the spherical wave contribution that travels at the group velocity of the incoming scattering target, scattering velocity. At this point, there's plenty of things we could say about scattering theory. We could go on to the theory of partial waves. So I haven't mentioned this so far in the course, and there won't be time in this course to cover phase shifts, but I'll just say some brief words about them. So when a coherent wave comes into a scattering event, you could describe a coherent wave as a cosine or a sine wave and some phase shift, yeah? If you have some relative phase reference. So an incoming coherent wave hits the target, and then sometime later it's a coherent wave again. But this is the picture that we've derived in this course. Now, in one dimension, we're so heavily constrained that we know that an incoming wave with momentum p has to be an outgoing wave with momentum p. There's nothing else it can be. So how do we even see scattering in one dimension? Well, there's only one thing that can change, and that's the relative phase between the incoming wave and the outgoing wave. So what could happen is the scattering event takes place, and then there's the outgoing wave, and it's undergone a relative phase shift with respect to the incoming wave. So this phase is the data that captures one-dimensional scattering. And you've probably done the calculation where you work out the stationary scattering solutions for this potential here, the step, right? You have some wave coming in, then there's this exponential decay through barrier 1, wave there, exponential decay, and you've probably worked out the phase shift between this out wave and this in wave in your first quantum mechanics course. Now this picture remarkably works in higher dimensions, except you have to appropriately change things, right? So in higher dimensions we have, of course, the incoming wave, which is plane, and the outgoing wave now, which is a superposition of spherical waves. And each of these spherical waves has an associated phase shift. So you can build a theory of phase shifts for these so-called partial waves, these scattered waves. That's one topic that we won't be covering in this course, but certainly I hope it's now relatively plausible how you would set that up. And another topic that we won't be dealing with in this course is multi-channel scattering theory, where you have n particles going in and n particles coming out. Now, to a large extent, you can reduce that down to this kind of scattering theory. You just say, okay, the closest two particles scatter first, and we model that by one of these processes. Then the next closest two particles scatter, then the next particle scatter. So you just break down an n particle scattering event into lots and lots of two particle scattering events. That's another topic that would take us a long time. Probably we'd have to do an intensive scattering theory course to really get into that. And the third and final topic, which is kind of interesting, but we'll also sadly be not covering, is true multi-channel scattering processes. For example, you have three particles coming in just the right times so that they interact all at the same time. What can happen? And the answer is astonishing. So I will just mention the key word, and then I leave you to research this yourself. It can happen that three particles come in at the same time and can form a bound state, even when each of the two particle bound states don't exist. So there exists very special three particle bound states called Efimov trimers. Now these things can exist, bound states of three but not two. And they have some incredible properties. For example, they're discrete scale invariant, so the wave function looks like itself when you scale it by a factor of a constant, but not anything in between. Very peculiar objects indeed. And for a while, people thought that these were just theoretical toys, but actually they contribute to physics in ultra-cold gases. So the presence of, or the ability to have Efimov trimers is physically observable. And it goes via the route of this scattering theory. So these are topics that I would love to have covered in this course, but really are specialist topics for another course. So in the remaining lectures, we'll be moving on to symmetries, and we'll be taking a look at Wigner's theorem about how symmetries are implemented in quantum mechanics. But for now, I thank you very much.